Hello there. Cosmic microwave background radiation and the Big Bang. That's what we're looking at here. So CMBR, it's called a CMB, cosmic microwave background radiation, is something that has been used or argued as the second of two pieces of evidence for the Big Bang. So we'll look at what that is, what it means, to further understand the Big Bang theory. Right, so can we take a picture of our Earth? And of course, there was a time before satellites where the only image of the Earth, I suppose, would just be you could take a photograph of your feet and then you could see the Earth, or you could try and get up a tall ladder, or go up a hill, or get a hot air balloon. But then obviously satellites we've come out, and that is an image of our Earth from satellites. So it was pretty big news when we got the first image of the Earth. And it's there's a beautiful image, you should look that up. It's called Earthrise, which is the Earth from the moon, and the Earth looks like a little blue marble. And some people say it was quite important for people starting to think of the Earth as a fragile thing. It looks all lonely in the blackness of space. Right, our solar system. Can we take an image of our solar system? Well, there's our best bet. When there's some alignment in the stars. But of course, in a textbook, it's these massive spheres right next to each other. But yeah, you certainly could. You could look back. So we've sent probes out to the edges of our solar system. You could look back, take an image. But famously, some of them will be less than a pixel in size. They won't even show up because they'll be so small from those distances. And we can only, with the naked eye, we can see Mercury, Venus, Mars, Jupiter, Saturn. But we can't see Uranus or Neptune. So some of the things will be too small from those distances. So not easy to get an image of the solar system that looks any good, but we certainly could. Next would be our solar interstellar neighbourhood. Alright, so no, we couldn't, we've never got out to any great distance. We're just taking pictures of stars. Look at this beautiful picture of a star. There you go, there's Vega. That's what it looks like in the diagram. That's an actual photograph of Vega. It's a blue star. Which one next? Sirius? No, Alpha Centauri. There's Alpha Centauri. So, yeah, we can take images of these stars. The Milky Way galaxy. Well, look. That is not a photograph of the Milky Way galaxy. Because we've never been outside of the Milky Way galaxy. The furthest probe we've sent is reaching the edges of our solar system, not our galaxy. There's hundreds of billions of stars in our galaxy. We are nowhere near sending something to the edges of our galaxy to take a picture of the whole galaxy all at once from the outside. Our local galactic group. Here's some images of our local galactic group. So these are all the galaxies that are close to us. Andromeda being the most famous. There's Andromeda. That is a photograph of Andromeda from our own galaxy. And there's the Triangulum galaxy, M33. Isn't it wispy and beautiful? There we go. We've zoomed out again to the Virgo supercluster. So the Virgo supercluster, here's our local galactic group in a cluster of other groups. There's the Virgo cluster, see? That's an actual photograph of it. It looks like a bit of a cluster of stars, but it's a cluster of galaxies, which is, times however many dots you thought there were by hundreds of billions. Our local superclusters, there's now the Virgo supercluster there, and then there's our local superclusters. So these are clusters of galaxies, clusters of galaxies. Don't even know what that means anymore. And there's the Sculptor supercluster. Isn't it insane that you can look up in the night sky, you will see a single dot, thinking it might be a star, and it's a cluster of galaxies. Unbelievable. And yet the dot next to it might just be a single star. So without the idea of depth and how far away things are, it's unbelievable how much different amounts of information are held in dots of light. And then zoom out again, we get to our local observable universe. Can we take an image of that is the question. Of course, that is just a diagram. Somebody's drawn a picture. You just ask the child to draw a load of dots. And there it is. There's the image of our universe. So maybe surprised by that. What I'd like you to do is imagine that you wanted to take a picture of the room that you are in. So you couldn't get the whole room in with one photograph. You'd have to have one wall behind you at least. But with a panoramic, so if you start at one end, just expose it for a longer period of time, and then move around the room gradually until you're back where you started, taken into a wide field of view so you can get the top and the bottom in as well, then it is possible. And that's essentially what we've done with our universe. We've looked in all directions, put the photographs together. Now, you wouldn't actually put the photographs together to form a two-dimensional image. What you've created is kind of a three-dimensional sphere around you. So that's what you'd have to do. The best way to view it would be to create a sphere around you, just like the room is around you. And then you could step inside it, like there's planetariums that you can step inside and see the stars all around you. But that's essentially what they've tried to recreate with this. So that's why it's not a flat shape. So that is the images of our universe. But it would be too much information, I suppose, if we just looked at all the parts of the electromagnetic spectrum. You might have assumed that we would look at visible light, but it turns out that we've chosen to look at a very specific type or frequency of microwaves. So why have we chosen to do that? Well, Wilson and Penzias, they were asked to make the horn antenna. And the horn antenna was to be used with, I suppose, NASA's first attempts at satellites. There's a satellite. It's a big balloon, isn't it, that was going to go up into space. Here's some information if you're interested. You can pause the video now if you want to read that. Otherwise, we will just talk about the balloon. So, yeah, it goes into space, and they would send up a signal, and then it would bounce off that in space, and then it would come back down. Well, why don't you just send it straight across? Because of the curvature of the Earth, you see. Radio waves, microwaves, they travel in straight lines. They don't follow the curvature of the Earth, so they need to bounce off something if they want to go around the bend of the Earth. So that's what that was designed to do. So it's for long-range messages being sent. So the horn antenna was designed to pick up those signals that bounced off it. And they turned it on, and it was receiving a signal. It was receiving information. And they thought, that's strange, because the satellite, or the balloon isn't even bouncing things off yet. So we shouldn't be receiving anything. So they kind of took it apart, they cleaned it. I think they moved out the pigeons that had moved into it, and they did all they could, and still they were receiving information. But at that same time, there was 3 people working in Princeton. Oh, and it was only 60 kilometers away. It's a tremendous coincidence. And they were preparing to search for what they thought was the remnants of the Big Bang. So, you do need to just be able to grasp redshift for this, I suppose. But the theory goes, there's an oversimplification of it, obviously, but the theory goes like this. When the Big Bang happened, none of the electromagnetic radiation could kind of escape. And then when it kind of became opaque, partly see-through, then the waves could suddenly escape, and all those heat rays from the Big Bang could suddenly escape and move out. Now you'd think surely they've gone by now, they've passed through. But the theory was that the universe was filled with these heat rays, and as the universe has expanded, those heat rays have expanded with the universe. So, yes, a type of redshift, but not because something's travelling away from us, more to do with something is expanding within it, so it's stretching out those heat waves. Now, hopefully, close your eyes and picture the electromagnetic spectrum, and hopefully you can see it. Gamma on one side, radio waves on the other. Next to radio is microwaves, and next to microwaves is infrared. Infrared waves are also known as a heat ray. So if you stretch a heat ray, you make the wavelength longer. So where's it going to go to? It's going to go to microwaves. So increase the wavelength of infrared and you get microwaves. So they had theorized that those heat rays, because of the rate of the expansion of the universe, they could work out exactly how much those heat rays will have been stretched. And they worked out the exact frequency of microwaves that the heat waves from the Big Bang should now be. So they were preparing to make something that would be able to search the universe for those heat rays that were now microwaves. And it just so happened that it was already made by Wilson and Penzias. They pointed it in every single direction they could in the sky, and it was detectable from everywhere they looked. So, because somebody had predicted it and then found it, that's often thought as a more solid way to kind of think a theory might be valid rather than finding something and then coming up with an explanation for it. It was predicted to exist and then they found it. So that was thought of as evidence for the Big Bang. So without the Big Bang, those heat rays would never have existed. It's still detectable everywhere. You see, everywhere you point this detector in the universe, but of course we wanted to get through the Earth's atmosphere so we could get a clearer picture. In 1989 we sent up COBE to observe these microwaves, Cosmic Background Explorer, and then we got that. Then in 2001 we sent up WMAP, which gave us that. And then more recently in 2009 we sent up Planck, which gave us that. That thing that runs through the middle is the Milky Way, which could be removed from lots of images. I think they leave it in very often because it looks kind of cool. So what does it mean? It means that wherever you look, so I think the lighter areas are where there's more heat. So that would suggest that there was more matter in those areas as the universe has expanded. So it's kind of showing the density of the universe. Some areas it's really dense, some areas it's not so dense. Now that doesn't make a lot of sense. If the Big Bang had followed the laws of physics as we know them now, matter should have been thrown out, or energy and matter should have been thrown out equally in all directions. But it turns out some directions got more energy than other directions. The thing that the phrase that's used to explain that is quantum fluctuations, and we don't really know why they exist. That we don't have a uniform universe equal in mass in all directions. So there's a lot of puzzles about the Big Bang, and it doesn't always seem to have followed the laws of physics. Could lead to the question, do the laws of physics have to be laws forever? Have they always been laws? Did the laws of physics change? Is it okay that the Big Bang doesn't follow the laws of physics? Anyway, all we're saying here is that this is the second piece of evidence for the Big Bang. So the Big Bang theory became a stronger theory because of cosmic microwave background radiation. The main reason for this, you won't get asked much about cosmic microwave background radiation. The main reason to learn about this is to deepen your understanding of the Big Bang theory. So that's it from me. I will link another couple of videos to do with cosmic microwave background radiation and the Big Bang, but it's essentially just a theory lesson for today. I hope that was useful. Thank you very much.